you.
All right, game on.
Thank you. He won't be.
Where's his giant biography? That's so we can read it without glasses. Barbara. Hi, Barbara. How are you? She only comes to the best.
Huh? We made it up as we went.
Charles
Long
Schultz
walks.
is the principal.
Like your jobs.
Correct. Remember when we used to work together? Yes. Good afternoon. Question? Already? Mr. Lager?
Oh, wait, I believe there's a question over there. Plaid shirt.
Yeah. It's got to be at work tomorrow.
Not going to happen.
My name is Craig Fox. I'm with ETC, although today I'm with LEDucation, and standing just behind me is Wendy Kaplan with Felix, and today with LEDucation. And we often horse trade which one of us gets to introduce whom for the 25 presentations that we've done. And we couldn't quite make up our minds which one of us wanted to do it, and then Kenny suggested that we just roast him. So we're gonna.
Over a spit.
So, in any event, couple of housekeeping things before we let Kenny do his masterfully done presentation, which clearly he did not write. There are on LEDucation.org some speaker evaluations that we would like you, if you should care to go and fill out. It helps us to get your impression of the presentations that we give every year and help us to keep the standard up, except for Kenny. Had enough, yes?
Yeah.
He's the one that suggested the roast. So if you would please go and fill those out, that would be really helpful to us and for you for next year's presentations. Also, if you need an AIA credit, if you have an AIA number and you've not signed up for the credit, at the tables by the main doors to that hallway, you can sign up for your credit. If you need a self-reporting credit, by way of that scanner as you walked in, you will get an email with your self-reporting credit document. Kenny Schutz is a principal at Focus Lighting, where he's the head of project management. He was a project manager for over 50 projects. Some of them were even successful. Ooh. Right, Brett? Including
Who was in charge for those projects?
I was. He worked for me. Including the Lumen Award-winning Royalton Hotel lobby, Bourbon Steak, Science Storms at the Chicago Museum of Science and Industry, and Yotel. Kenny has taught at Vassar College, Connecticut College, and NYU. He's a member of United Scenic Artists of America, Local 829, the IES, as well as being a project management professional and an NCQLP lighting certified whatever he is.
Whatever they call that.
In any event, do you have anything you want to say about, for Kenny?
We're really, really glad to have all of you come and hear his presentation.
Yes.
Kenny's a wonderful speaker, and I'm sure it will be a great presentation. Thank you.
Yes, thank you.
No pressure.
Kenny Schutz.
All right, thank you. All right, good afternoon, everyone. I'm here to talk one designer to another. Okay, all the stuff about credits. And the learning objectives today will be to recognize and avoid two of the leading causes of color variation, identify the characteristics, pros and cons of different dimming and control methods, understand the role of the driver in dimming performance in flicker, and to learn all along specific strategies for designing successful specifications and lighting designs. I'll start off by saying that I actually don't have that much to say that's new in terms of how to use LEDs. Much of this has been said already, a lot of it right here at LEDucation's, but most of what I saw and read was written by manufacturers or reps or even a scientist, and I wanted to speak as a designer to other designers and specifiers. I wanted to tell everyone about how I got to the point where I could stop screaming, "I didn't sign on for this." About all the mistakes I've made, and about the lessons my company has learned in the last 10 years. But then Craig told me I had to keep it to 45 minutes. So LEDs have transformed the lighting design and manufacturing industries, that goes without saying. LEDs present the designer and specifier and distributor and installer with new challenges because they are more complicated than traditional light sources. We're going to talk about 3 of these challenges. Color, by which I should say, I really mean white. What understanding do you need to have in order to keep it good and consistent on jobs? Dimming, how not to mess it up, how to get what you want. And flicker, what causes it, how do you avoid it? Dimming and flicker will require that we talk a little bit about drivers. And I chose these topics, these 3 out of many really, because these are the top 3 that we've had to wrestle with at Focus Lighting for the last 10 years, and we continue to do so every single day. Why? Well, my point of view is that if you want to guarantee success for your lighting designs, then you have to think of yourself as being responsible for it, for all aspects of it, from concept to commissioning. So here's the bad news. In the age of LEDs, what that means is you have to dive deeply into some of the nuts and bolts. You can't always just leave it to others. In a nutshell, and please keep this in mind throughout the presentation, my subtext really is that you have to learn and you have to test. Those are the absolute essentials for success. The rest, as the rabbi said, is merely commentary. What's the good news? Well, LEDs have, of course, given us great opportunities, thanks in part to their size and controllability, all while reducing power consumption, maintenance issues, hazardous material use, and the like. So here we go. Starting with color. An actual quote from a job that we were discussing in the office with an interior designer. We expect color to be consistent. Once upon a time, we used to be able to go to the store, buy a light bulb in 60-watt A19, let's say, and we expected that that replacement that we bought a year later would look the same. And that's not necessarily a reasonable expectation to have with LEDs. Quick mock-up I did in the office. These are 5 different 120-volt AC Cove fixtures from different manufacturers, all 2700 Kelvin, all on paper, about the same light output. And with the lights on, it's a little hard to see, but they're 5 distinctly different colors. Pink in the middle, green and different variations off to the sides. What's going on? Well, a couple things. First of all, white is, of course, not a color. It is a range from warm to cool that's measured along a continuum called the correlated color temperature. It's measured in degrees Kelvin. And that is plotted on the graph on the right is the CIE chromaticity diagram. And what it allows us to do is graph color on an XY axis with saturated colors towards the perimeter and white being arranged in the middle. Along that arced line, that is called the black body curve. It is a theoretical construction that physicists have come up with to place those different warm and cool values of white on this graph. And warm is somewhere towards the lower numbers, anything below 3,000, let's say. Excuse me. Cool is somewhere above 4,000, and neutral is somewhere in between. The lighting facts labels that we now have show that as well. Going back one sec, the next dimension, however, it's not just left-right in terms of warm and cool. CCT is not the same as chromaticity. It doesn't speak to that at all. And so where you have the 4,000 line here, any color plotted on this graph along that line is 4,000, regardless of whether it is relatively green or relatively pink. It's still 4,000. So that is another dimension of variability within any one definition of white. Okay. CCT, degrees Kelvin, is also defined on the manufacturing level, or for manufacturers, by ANSI as being a range. What you see, the 27-degree Kelvin you see on cut sheets is nominal. The real measurement per ANSI is it's a target that has its center at 2725, and it can be plus or minus 145. So anything from about 2580 to 2870. And while 145-degree Kelvin may not seem like a lot, at the two extremes, you're dealing with a range of 290 Kelvin just within what is on paper 2700 Kelvin. So with color temperature, the color of that white may not match manufacturer to manufacturer, product to product, even within a manufacturer, one version of the product to the next, and one order to the next. And this is all without addressing the effects of time, heat, phosphor quality, manufacturing quality. These are post-specification manufacturing issues. So how do we get any color consistency? Well, that's the role of binning. On the manufacturing level, making these LEDs produces unavoidable variations. In fact, there are 3 types of variations that are binned for, but we're going to focus solely on the color. Binning is simply sorting those LEDs to minimize the variation, and the wider the bin, the faster the lead time, the lower the cost, the faster the lead time, but there'll be more variability. ANSI defines color bins as parallelograms that enclose a 7-step macadam ellipse on the 1931 CIE color space. Okay, that was a mouthful. Let's unpack that one. So first of all, we already know that this is the 1931 CIE color space. A macadam's ellipse is drawn here. These are actually larger than they really are, but they are commonly represented larger to make it easier to see. And the macadam's ellipse is really nothing more than a method of documenting how far one can stray from any given color, say that particular green, how far you can stray, anything within that ellipse, before perceiving a difference. The larger the ellipse, the more people will see the variation. You can have different size ellipses. They go from 1 step, which for the statistics mavens is one standard deviation and is generally accepted as the common person, the ordinary person wouldn't be able to perceive any difference. And then they can get larger, 2-step, 4-step, 7-step. And at this, most LEDs used to be binned in the 4 to 7-step level. That was, I think 7-step was the standard for fluorescence back in the day. Now, here is the black body curve that I was showing on the colored graph. These are the parallelograms that ANSI defines, so your macadam's ellipse your 7-step macadam's ellipse would be in here. So with a color bin, you can take the entire 7-step macadam ellipse, which would have plenty of variation within it. You can take a portion of that ellipse and have a tighter bin with less variation, or you can really go hog wild and have tiny, basically I think this is 1/16, which gets you down to a 1 or 2-step macadam's ellipse. And upstairs this morning, I saw some manufacturers who were saying, I know of at least 2, who say that they will bin their LEDs to 1 macadam's ellipse, 1 bin, 1 macadam ellipse, and you can even specify which bin you want. The important thing here is to work with manufacturers who know and track what bin was used so that they can reproduce it later whenever maintenance or design changes require. With the binning then, after they've got them sorted, they have to figure out how to use them. And one way to do it, which we've kind of alluded to, is to buy 1 bin and metaphorically throw away the rest, or put it into Christmas lights. That's easy to do, but it's the more expensive way to do it and leads to longer lead times. At the opposite extreme, a manufacturer can buy a large production run and develop the expertise necessary to mix the different colors together to get a target one. So for instance, if the green box were the target color that they're looking for on their strip or downlight or whatever, instead of necessarily just buying only that one, they could buy this and this. They'll mix together if placed side by side, and they can still achieve the specified color. So with color, what do you have to do? Well, first you have to understand what color temperature really is so that you have the right expectations, and get into the details of the fact that it's a range from warm to cool and a range from green to pink, that it is defined as being a range in and of itself, and know the manufacturer's binning strategy, because that'll make a difference to you down the road when you've looked at the sample 1 year and you come back a year later on the job. Will it look the same? Will it look different? So a recommendation would be to specify manufacturers who can and will track and repeat a bin. And it's also helpful to find manufacturers who will offer a color shift warranty. They're out there. I showed a lot of graphs. Don't trust graphs. Don't go by graphs. Use your eyes. That is your resource. That is your resource. That is why people hire you. Use them. Trust them. Look at samples. There's no amount of paperwork that will substitute for that. And get the support from the manufacturers and the reps and your clients so that you can have the time and resources with which to do that. It's in their interest. Dimming. Okay, this really happened. I was there. It was scary. I'll just read it. It was great. It was really great. This guy who's a VP of, and built lots and lots of casinos, and he's no nonsense, and multi-million, if not billion-dollar projects. And he just turns to the design team and he says, I'm sick and tired of my LEDs not working. They flicker, they don't dim, they look bad. I'm constantly being told it'll work fine, by which I think he meant distributors and reps and alternate manufacturers. Because he added that, but when I asked the designer, they just say, well, you didn't buy what I specified. So fine. I'll guarantee that you'll get what you specify. You have to guarantee it'll work. And then this is a question I get many variations of. Okay. Right? Seems perfectly reasonable. Right? I mean, we used to put 20, 50-watt MR16s on a 1,000-watt dimmer, D rating aside. Why can't I put 142 LEDs? I mean, isn't that what it's all about? Not so much. One of the things, the first thing with dimming is that there are no standards that exist. So you can't necessarily get the right dimmer LED combination, and for that matter, the LEDs, the dimmers rather, all existed prior to the LEDs. The dimmers were not designed around LEDs with only a few exceptions. To get the right dimmer, you have to understand the role and importance of the driver. And I've found in discussing it with colleagues and clients and installers that the most important thing to do to start the conversation is to unpack and separate dimming from control. Now, dimming is regulating the amount of electricity that is delivered to the fixture, the driver, whatever. However, it's not necessarily done with a dimmer. Therefore, I believe that the better term to use is control. With control, you're sending a signal, usually low voltage, but not necessarily, to a device. That device could be a dimmer, but it could also be an LED driver. And that signal tells the device how much electricity to deliver to the LED. Well, I guess I should have clicked on that animation sooner. So we start with control, and control can talk to dimmers. The dimmers regulate the power to the driver. The LEDs will have the corresponding light output. And this is also known as line side dimming or primary side dimming. Or the controller can be talking to dimming drivers. With the dimming drivers, non-dim power comes in. It bypasses the dimmer. The driver then regulates the power to the LEDs. The driver is doing that in response to instructions from that low voltage signal, and this is called load or secondary side dimming. The controller talks to the dimmers, and there are basically two types of dimmers, analog and digital, but analog is in gray because that's the rheostat from the old days, which was continuously variable and inefficient and has gone the way of the dinosaur. The modern dimmer is actually a digital solid-state device. It switches on and off 120 times a second, which I'd like to linger on that thought for just a second. It dims by switching the current on and off 120 times a second. It's flickering it on and off 120 times a second. So hold on to that thought. With the old incandescents, we didn't see the flicker because the filament would heat up and respond slowly, smoothing out that variation. LEDs, God bless them, respond instantly. At this moment, we have to take a brief digression into dimmers. Oh, sorry. That was just saying what I said. So with dimming, I was once warned that if ever I should speak to a room full of people and use terms like MLV or reverse phase, that I should bring enough tequila for everyone, which I didn't. But it occurred to me that one of the things that makes it seem much more difficult than it really and truly is that there are lots of terms being used out there that all mean the same thing. So I'd like to try to help with that. So when you're using digital dimmers, whether it's in a wall box or a dimming panel, you're talking about a phase cut dimmer or a triac, an SCR, or two-wire dimming. These break up into two major categories: forward phase and reverse phase, otherwise known as leading or trailing edge. Among the forward phase, you have two kinds, incandescent and MLV, or magnetic low voltage. They're similar, but they're not exactly the same. And on the reverse phase side, you have ELV, electronic low voltage dimming. With forward phase, those are the most common on the market, and they've been around the longest, but they're not necessarily the best suited for LEDs. Reverse phase might be better for them, but they are, in fact, less common and are more expensive. And for anyone doing retrofits, they might be unusable because the neutral wire is required. My house was built in 1925. I'm lucky to have J boxes, never mind a neutral wire in my walls. The difference between forward phase and reverse phase. Okay, hold on, here we go. So AC current is basically a sine wave. The A meaning alternating, and 120 times a second, at one moment the current is rising and then falling, and then it's rising again, but now from the other direction. It's now alternated direction. It's rising and it's falling, and it continues to do that repeatedly. The green is undimmed. The switching, the on and offing that digital dimmers can do can happen either at the front of the hump or at the back of the hump. And if it's done at the front of the hump, then it's forward phase, and if it's done at the back, then it is reverse phase. With this switching method of dimming, the amount of time that it is spent off or on results in a corresponding output from your lamp, LED, whatever. So if it is off for half of the time and on for the half of the time, then it'll be dimmed to about 50%. Okay, enough about that. Now, yeah?
If it's switching on and off
not sure.
Like if it's switching 120 times a second and that's on at full?
Right, it's crossing that zero moment for only an instant. With the dimming, it's extending that amount of time. So I mentioned that dimmers were actually built before the days of LEDs, and so a couple of things that we thought we knew about LEDs about dimmers have to go out the window now. This is from a major manufacturer's application note buried somewhere on their website, on their copious website. And they state that many of our products provide minimum and maximum load ratings in watts. These ratings are based on traditional light sources and do not apply to LED or CFL loads. They go on to say that the minimum loads for LEDs and CFLs are described with a minimum number of lamps, and that this value is determined on an individual load basis and may be different for each specific lamp model number. What that is engineer ease for we don't know. And the only way, and there's no formula we can use to figure it out. The only way we can do that for you is to test it. Got this email from a lamp manufacturer. God, I wish I could call out these people. We recommend derating the dimmers because of the inrush current. I'll explain that in just a second. With a factor of 5. This means that for a 500-watt dimmer, our estimate would be a maximum 100 watts of LED line voltage lamps. This was an email about par 30s. So what they're saying is, if the wattage of the LED lamp is 20, when you're using it with a dimmer, count it as 100. And that's why you can't have 140, that's one of the reasons why you can't have 142 7-watt lamps. Similarly, another manufacturer was telling us that due to an electronic characteristic known as repetitive peak current, more on that, which results from inrush current at the phase cut, blah, 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 our downlight should be treated as a 75-watt load for sizing purposes when used with dimmers. That 75-watt load for use with dimmers, on the cut sheet, that's a 15-watt downlight. So an LED so about inrush and repetitive peak. Here it is in a nutshell. An LED may draw, for instance, 10 watts on average, but the driver produces momentary electrical stresses that are larger than the average. These are inrush current, and that happens at startup when you turn the thing on, or repetitive peak, which happens at every half cycle, every time that sine wave crosses 0. There's that tiny instant of being off, so there's that tiny little extra instant of inrush, called repetitive peak. These larger stresses impose a lower limit on the number of LEDs that a dimmer can handle. That's it. So, back to dimmers. They're digital. They're forward and reverse phase. Forward and reverse phase dimmers can be used to power dimmable LED drivers. And the important thing here is to make sure that your LED driver matches the dimming method used. There's no one answer as to which one is better. The manufacturer will generally determine that for you. Sometimes they'll accept both, either or. But once the selection is made, then the dimmer must be of the same type. And that is an argument right there for coordinating controls and fixture specifications early. 2 days ago, actually, okay, brief digression, I got a telephone call from an electrical contractor who sometimes calls me to ask him, to help him make sense of specifications that he gets on jobs that aren't ours. And he was telling me about this residential job where he sent me a cut sheet for the fixture, and he just happened to, in an offhand way, mention that the dimming manufacturer was going to be there doing a site survey, and it was an old wireless dimming system. And at no point was the fixture specification mentioned in that meeting. And the fixture was ELV or 0 to 10 only, and the system that he had, I knew, was only forward phase. So right off the bat, there was a specifier and a control system completely uncoordinated. With control, you can talk, so with control, you're talking to either dimmers or you're talking to dimming drivers. And again, these are powered from a non-dim circuit. They get the instructions from the controller and they handle the dimming itself. What's great about dimming drivers is that compatibility with the dimmer is not an issue. Why? There is no dimmer. Okay? It's just one of the control methods being used. You can have, your control signals can be either analog or digital. And the two that I'd like to mention are 0 to 10 and DMX. Excuse me. These are by no means the only ones, but for my money, the two primary ones. The next three slides have a chart that I actually kind of put in here thinking that if anyone downloaded it later, it would have a lot of information. But for now, all I'd like to do is jump down here to start the comparison by saying, sure, two-wire dimming is the simplest. It's what we've been used to for the longest installers as well. 0 to 10 is a little bit more complicated because it adds an extra pair of wires. And DMX is, relatively speaking, the most complex. It adds additional wiring as well, but there are more conductors and more equipment required. With two-wire, your zoning, how you have your control set up, is going to be determined by the power wiring. With 0 to 10, it's determined by the low voltage wiring, and with DMX, it's actually open and flexible with only a few constraints. There's some, with low voltage and the wiring requirements, you can't do just anything. There are standards that speak to your maximums and minimums. I put those there for later, should you choose. And a few thoughts about the different methods combined is that with two-wire dimming, like I mentioned, because they were not originally designed for LED loads, you have to do that testing, and most often you'll find problems occurring at either low levels or with small loads, and that's where testing is absolutely essential. I can't say it enough. With 0 to 10, there are two different standards that define how it's done, and you have to make sure you have the right one and that you're not mixing them. I'm told that there are these theoretical inconsistencies that you can get with levels being different or fixtures rippling their way on instead of coming on all at the same time. And from what I've been able to determine, mostly that's a result of a wire of too small a gauge being used instead of a larger gauge wire. You need a relay to be able to turn the power off to the driver. DMX, because it is open in terms of how you zone these things, zone the fixtures, you have this added step of telling each fixture what its number is, its address. So sometimes it's a real drag to have to go to each fixture and set that number. With some systems, there are now remote ways of doing it called RDM, so you can just be back at the controller and set all of your levels. And it too requires a relay to kill the power to the driver. For the installer, two-wire is the easiest. 0 to 10 has the additional wire and the polarity matters. Normally that'll be a purple and a gray. I once saw an electrician try to pull it with two blues. I walked up to him and I said, great, you know, black, white, green, I got it. What are the two blues? That's your 0 to 10. Which one's the positive? And he got back up on the 40-foot condor. Yeah, that was, it was, and I'd caught him about only a third into it, and it was 2 days of redoing. DMX, similarly, it's not just polarity. There are anywhere from 3 to 5 wires involved, even more if you're using Cat5, so the colors matter. And in both cases, your proximity to line voltage wiring matters. The line voltage can interfere with the low voltage data. Okay, so, yeah.
Sorry, what did you mean by standards? Under the
Oh.
standards?
Yeah, so, where is it? There's this,
Oh, those standards, okay.
right, yeah, sorry, there it is. So there's an IEC standard that basically explains to all the technically inclined what exactly constitutes 0 to 10 volt control, and then USITT has created one for DMX. Makes for, if you have trouble sleeping, highly recommended. Okay, dimming and dimmable drivers. This is one that we used to struggle with a lot, but the cut sheet said it'll dim down to 10%. 10% of what? So let's back up for just a second with before we get into drivers, let's just back up for a second and talk about LEDs. LEDs are low voltage, DC, current-driven devices. So a driver must transform the line voltage that comes out of the wall to low voltage, rectify, change the AC to DC, and regulate the current going to the LEDs. It must also dim without flicker and do all this smoothly while compensating for fluctuations. A driver is a very busy piece of equipment. The LED driver is the #1 primary determinant of your LED performance. And that performance would be your dimming range, your curve, the on and off behavior, and how much flicker it has. The best that a dimmer can do is not make it worse. That's an important point. For a long time, we used to try to match dimmers and drivers and try to find, oh, maybe this dimmer will make that driver better than it really is. After a long time, it just became clear that the best that a dimmer can do is to do no additional harm, so to speak. About that 10%. So manufacturers will quote measured light numbers, but we as designers and consumers are more familiar with perceived light. Reducing the amount of current that an LED receives reduces the light output in a roughly linear fashion, meaning you reduce 50% of the current, you get 50% light output. But because the human eye compensates for low light levels, the relationship between measured output and the perceived output is not linear. It follows a graph that is more logarithmic. And therefore, by the way, God bless the lighting handbook for this graph. A 10% driver will have a perceived light output of 32%. A 1% driver will have a perceived output of about 10%, and a 0.1% driver will have a perceived output of about 1%. So with control and dimming, what to do? First of all, decide at the beginning of the project how much dimming performance you really need. Are you really going to drive yourself crazy trying to get that perfect down to 1%, or can you just take it easy with the 10% driver? Which dimming methods will be used, like my story, and determine compatibility early on. You should specify the drivers you want and need, and this is not a place to go cheap. I mean, sure, on my house, I'd rather spend the money on the paint and the furniture, not on the roof and the foundation, because I don't look at the roof and the foundation very much, but it's not the place you want to go cheap. Use brands you trust. Don't go for the newest, bright, shiny thing, as the organizers of LEDucation don't like me anymore for saying that. And ask manufacturers about compatibility. Get the manufacturer's help and test, test, test. Flicker. Okay, so the U.S. Department of Energy did a lot of research and published reports about flicker, and it amounts to this: flicker is bad. primarily, it's a function of the LED driver. That is what is creating the flicker. Measuring and reporting flicker is not standardized, and the Department of Energy has also told us that in the absence of flicker metrics, LED systems should always be visually evaluated. In other words, we don't know how to, which is more engineerese for, I don't know, test it. And I love throwing that sentence at manufacturers and reps when I'm hawking them for more samples and more mock-ups. Dimming an LED source can increase or induce flicker. That's that switching we were talking about before. And all AC powered sources flicker because AC, 120 times per second, is off just by its very nature. An LED, if it gets real DC current, will never flicker. That is the graph for a DC source, and it doesn't go anywhere near the zero line. AC flickers because it's off here and here. And what drivers are doing is converting this to that, which is not so easy to do. Visually, here's what it looks like. You start with the curve, the rectifier, which converts from AC to DC, takes this portion of the curve and flips it to the top so that even though it's always changing the amount of current flowing, it's always flowing in the same direction. By staying on this part of the line, it's representing one direction, not alternating. Then the driver will have additional electronics, filters they're called, most commonly a capacitor, that then smooths out the humps so that instead of it flickering, if I were to use my hands to try and show it, instead of flickering all the way down to 0, which would be 100% flicker, it's now flickering like this. And the less motion to that flicker, the less percentage to it, the harder it is to see. Here in pictures is what I've been talking about with dimmers, how digital dimmers cause flicker. There is a undimmed sine wave. Now, a forward phase dimmer is taking off, say, 20%, and so this one dot instant of a moment of 0 is now this little bit of time, and you dim down lower, and now it's a much longer amount of time. And so the amount of time it spends off increases your likelihood of seeing that flicker. Analogously, there are some LED drivers that, with LED drivers, there are two methods used for dimming the LEDs. Again, we're not talking about dimmers, we're talking about the drivers. One of those two methods is called PWM, or pulse width modulation. We're taking the straight DC line and we're chopping that, switching that on and off, so that it's on here, off for a moment, on here, off for a moment, and because it is off for an average of about 70% of the time, it's a 70% output perceptually. Conversely, you can have an average of 25% visually manifested by having it off for 75% of the time. And again, that's another way to increase your likelihood of seeing flicker. There's some other causes. There are many causes. Some of them might be not meeting the minimum load requirement of a dimmer. And then after that, you get into all these fuzzy ones where people will start giving you all these words that maybe don't mean anything about why it's not working. Dirty power, harmonics, gremlins. Now, in order to avoid flicker, the first thing you have to do is see it. And not everyone has the same ability to see flicker. I'm not so good at it myself. There are some tools, light meters, that will sense it. At Focus, we have a finely tuned, very sensitive, super accurate, highly calibrated method of doing this. Her name is Kelly. But a way to cheat at it is to take a pencil and wave it, take your hand and wave it. Sometimes if it's small enough, I'll just pick up the strip and shake it. Or you can use these spinny tops that a couple manufacturers started giving out. I remember the year that they first started giving these out, 1 or 2 manufacturers, pissing off all the other manufacturers. And basically what you're looking for is when you're waving your hand or pencil, you're looking for the blur. If it's a blur, there's no flicker. If there are distinct lines or distinct dots of the diodes strobing in front of you, as it were, if the pattern becomes more about white and black and white and black and less of a gray blur, then you have flicker. I've seen people also sometimes just whip out their camera phones and use that as well. They all work. To avoid flicker, you have to know your tolerance and your application. Task light would be less tolerant of flicker than perhaps a cove, for instance. Generally speaking, however, what you're trying to do is find fixtures that give you high frequency, meaning the flicker is happening really, really fast. So fast that there's no chance of you being able to see it. Or the modulation percent, or percent flicker as it's often called, is low. So in other words, this would be 100% flicker, while this would be only 10% flicker. So that would get you down here and in the green range, which is where you want to be. This information is generally not available on the cut sheets. You have to talk to the manufacturers. And some dimmers can, depending on what you're using, have methods for adjusting them to ameliorate the situation. One manufacturer has a little knob on the inside where you can set a low trim. Some of the more advanced ones, you can actually reprogram the entire dimmer to have a different curve and respond differently, thus avoiding flicker. Again, the only way to get around it and away from it is to do tests and to do mock-ups. So at the risk of beating a dead horse, the big takeaways for today are test, test, test. Trust your eyes. There's no good alternative. We make our living with our eyes. And you have to get the support that you need from your clients and your manufacturers, because it's in their interest for you to be able to specify products that will perform in ways that will make them comfortable and feel good in their space. You have to specify. I believe very strongly that the LED and the driver and the controls and dimming have to all be specified by the lighting designer. One of our mantras at Focus is, we're specifiers, we're specific. And we should be complete as well. Anything else is leaving it to chance. Like I mentioned, people send me drawings and specifications from others. I have redacted these to hide the identity of the guilty. But here is one specification which goes pretty well to telling you what it is you need to get, and there's a full manufacturer and part number here. You know you're at 24 volts, it's telling you you're at 24 volts, so you know you're at low voltage. But it's not really talking about the driver. Well, there is this one helpful note. Contractor to provide all parts necessary for a fully functioning installation of all products specified. Okay? Guaranteed, this specifier will show up after the walls are closed and the furniture is in and say, wow, this dimming really sucks. Okay? And they get what they specified. Here's another one. It goes a little bit less far even. And then here's my favorite. Lighting legend, LED lights. It also has the curious notion of a ½ a watt per linear foot LED fixture. I don't know what that is. And then it says down here, all LED lighting to be dimmable. And let me just put that note in context. Here's the drawing. There's the note. So in closing, as specifiers, we need to take charge. I believe we're the best situated to see the entire horizon of a project. And with that position comes the ability to coordinate and communicate with everyone, architects, to electrical contractors about anything and everything that impacts your design. We're the experts, and we should act as such. Thank you. So I really went over. Any questions? Yeah.
Who do you recommend speaking to at the manufacturers about these technical things? Most salespeople don't dive that deep. So you ask for a product manager, you ask for the smartest guy in the building.
I try as much as possible to get past the salespeople to the engineers or product managers. Absolutely. Oftentimes, I have to do it with the reps' support. You know, they want to be involved. That's fine. They shouldn't stand in the way. And they shouldn't be a go-between. So you first.
Do you find yourself specifying, now that everybody carries a high-speed camera in their pocket, do you find yourself specifying fixtures for that, with that in mind?
No.
As far as like high-speed?
No. High speed at that level is really if we were doing a television studio, I'd really be thinking about that. But to date, we haven't really designed for a camera, let's say.
If you have a bi-level lighting in a fire stairwell that's supposed to go down to 50%, does it not seem like 50%? Because you said 10% seems like 53%.
I don't do a lot of bi-level dimming, so I can't say that I know for certain, but I believe that a bi-level dimmer, a bi-level ballast, when they're talking about 50%, they're talking about 50% current, which for an LED is not 50% visual.
What is it? Feels like more?
Feels like much more.
Feels like more. Okay.
And by the way, for the question before about the camera, there was one instance where we were working on a museum installation where we knew there was going to be a photo opportunity, and there we actually took the hit and went incandescent just to avoid that, thinking about that. Yeah.
Do you have a sense for when the flicker is obviously slower than AC currents, what the culprit usually is?
That would be, okay, it could be a number of things. Minimum load is one that comes in, and sometimes the electronics in the LEDs themselves, they're not getting enough voltage, and so they're being starved and they can't do their work properly. So at the very low level, when you're not seeing the flicker, but you're seeing like a waver, okay, that is the electronics that are inside not getting enough current, enough voltage, is what it feels like it usually is for me. I'm not an electrical engineer. I don't even play one on TV.
In your discussion on dimming, has it ever come up when you're specifying a product that somebody wants something to correct for the nonlinear perception? So for example, if you're adjusting the wall switch and you want that to linearly correlate to the
Yep.
that you perceive, does that correlate to the standards that you identify for 0 to 10 volt?
So some dimmers and some drivers will allow you to reprogram the curve, because this is a curve for visual perception, but just for a moment, forget about that and just look at it as a logarithmic curve, just a generic logarithm. Some dimmers will have a linear curve, meaning when they do the dimming, 50% results in 50% output. Sometimes it'll be logarithmic. And what you can do is you can with certain dimming equipment, you can reprogram the curve to make it do different things at different points in the fade. And what's kind of great about that is with a curve like this, what sometimes happens is you're getting a lot happening at the beginning, and then up at the end, very little happens. Like, I'm sure many of you have seen it where you're dimming for the first, from 0 to 20, it seems as though most of the action happens, and then from 80 to 100, you're kind of like, there's almost no difference. What's going on? That is a function of perception and the dimming curve, which when you have the opportunity with the equipment to specify equipment that allows you to reprogram it, you can do that.
Does that usually happen at the wall switch level or at the driver?
It doesn't happen at the wall switch level. It can happen at the integrated dimming system level, and with certain drivers, you can actually, I can think of one particular driver, I wish I could say it, but it's one of those really, really good ones with 0.1%. You can actually set it to be linear or logarithmic. Yeah.
Does this mean that constant current is more vulnerable to flickering than constant voltage? Or?
No, constant current and constant voltage actually refer to two different things. I actually had a slide for this, but I deleted it. Okay, so real quick, constant current, constant voltage. I'll make it real easy. Constant current you use when you have individual LEDs, either a single one or a fixed number wired together. Okay, so if it's round, so to speak, it's going to use constant current. If it's going to be linear and you're not really sure because 1 minute it could be 4 feet and another minute it could be 20, if it's long, it's going to be constant voltage. Both of those methods do not speak to dimming. Okay? What speaks to dimming is CCR and PWM. And okay, and with constant current reduction, it's actually most analogous to old analog rheostat dimming. It just reduces the voltage. So if this is where we started, and now the driver is putting out this many milliamps, it's just reduced it. Whereas PWM, the amount is, the voltage stays constant, or the current stays constant, but it's being chopped up into segments. But it's used in both, yes. In fact, you can have constant current reduction and PWM in the same driver and in the same fixture. There's some linear fixtures upstairs that do that, and one of our favorite drivers does that. And there's technical reasons for it, but the quick version is PWM if PWM is done fast enough, it's better at getting deep dimming. Constant current reduction has two problems with it. One, it causes color shift, and I don't know why, so please don't ask. And two, because constant current reduction is reducing the current, it can get to a point where there isn't enough electricity going to the LEDs for it to stay on. Whereas if you can keep it up there but just chop it, the LEDs will just happily flicker.
Thank you.
Yeah?
So with all this complexity, what percent of the lighting that you specify is LED now, and how has that changed over the last few years?
Wow. Decorative aside, I would say it's 100% at this point. And
what was that like 5 years ago?
Probably something like, what, 60% 5 years ago? And 10 years ago when I started, it was almost zero. So Craig mentioned that I did the Royalton renovation. On that job, oh boy, that was fun. Those are the days of 75-watt par 30 socket strip on 6-inch centers. Yes. And we had one LED fixture. It was a linear, and it was there not because we were trying to save energy, but because it was a tiny, tiny shelf detail, and that was what would fit. Now, everything is LED, and we get to use a halogen or incandescent source. Basically, we limit it to decorative, because we feel as though that's really what you want to have sparkle and din-dam beautifully and all of that. And I run around the office saying, okay, let's eat our vegetables on everything else so that we can still have incandescent for our decorative and stay within code. But even now, we're losing that fight too. And so we're actually here at the show in force trying to find the best dimming LED filament lamps and decorative lamps ourselves. Yeah.
Yeah, so that's a hard thing. So for like a Park Avenue lobby chandelier that still has the incandescent bulbs, is there a reasonable LED bulb that would be warm enough and attractive enough to be paid for?
That's a tough one. No, again, I think the answer is no. Yeah. Or just barely. And you have to kind of redefine what you mean by acceptable a little bit. God bless jobs where they're historical and so energy code doesn't apply. Love those jobs. By the way, since everyone seems to be staying around late, and that's great, thank you. One thing that I always ask the people that I'm working with is, how many of you hated trigonometry and are afraid of a sine wave and think that it's just this theoretical bit of nonsense that has no physical application in real life? Okay, don't raise your hands, it's okay. But it's actually a thing, and it represents a very real physical thing. And I got a slide for that. Okay, so to make AC current, essentially what a generator is doing is rotating, say, at least metaphorically, a wire inside of a magnetic field, okay? And the magnetic field has a plus and a minus side. And when that wire flips, the relationship between the plus and the minus and the two wires changes. So to generate electricity, there's this circular motion. And the only thing a sine, by the way, look at the green curve, ignore the purple one. Okay, that's showing you cosine. Sine is bad enough. So what a sine wave is basically showing you is a circular motion graphed over time. This axis is time. And as the generator is spinning, it starts out with no electricity being generated. When the wires are in a 90-degree relationship to that magnetic field, the most electricity is being generated. Then it goes back to this flat thing where there is no electricity being generated. And then it continues on, but now what was on top is now on the bottom. So the plus and the minus relative to this wire are different. So it's now flowing in the opposite direction. When it gets to 270 degrees, 3/4 rotated, again, it is the most amount of current that you're going to get, but in the opposite direction. And then it comes back up to 0. And then it just keeps on repeating it. That, when I finally got that, which happened only a year ago. Okay, I'm a theater guy. I didn't start learning or knowing any of this. This was years and years of late night sleeping, which probably, if I had stayed awake, would only have taken a couple of hours. But once I understood that this sine wave is something very material, it's a circle graphed over time, suddenly worlds opened to me. And I hope maybe for you too. Anything else?
That should be in 8th grade textbooks.
Yeah, right there. Okay. Thank you, one and all.
Kenny, I never knew why it was called sine. I know cosine is trigonometry.